Dear students, today we are going to discuss about direct sequence spread spectrum system with coherent BPSK. So we will be discussing about the characteristics of that system. Okay. So first characteristics is processing gain, second one is probability of error, third one is antijam characteristics or jamming margin. Let us see what is processing gain. Processing gain is defined as the gain achieved in processing spread spectrum signal over an unspread signal. And processing gain is the ratio of the bandwidth of the spread message signal to the bandwidth of the unspread data signal. So in the case of spread spectrum system, we will be spreading a unspread signal. So the gain achieved during that process is called processing gain, and processing gain is equal to bandwidth of the spread signal divided by bandwidth of the unspread signal. It is unspread. Okay, there is a spelling mistake. So let us see, suppose if the message signal B of t is given like this, and this period is called TB, that means period for a single bit is called TB duration, and let this be the PN sequence. You can see this is 0 0 0 1 1 1, then 0 0 1 0 1. That means up to this point the PN sequence is same, then it is repeating. So for each of this pattern the time period is TC. So you can notice that TC is less than TB. So NTC will constitute TB. Okay. So here when you are obtaining the spread signal by multiplying this B of t with the C of t. Actually we are modulating it with the PN sequences. So this the signal will be spreaded. Okay. So when we are multiplying this with this, you will be getting the sequence like this. So minus 1 multiplied with the minus 1 give you plus 1. Then minus 1 multiplied with the plus 1 will give you minus 1, and minus 1 multiplied with the minus 1 will give you plus 1. Minus 1 and plus 1 give you minus, minus and plus give you minus, again minus, next is plus and minus give you minus, like that. This is the sequence. Okay. So whenever the polarity of B of t and C of t is reversed, then the output will be minus, and if polarities are same, then the output will be plus. So this is the sequence we are obtaining. So from this you can notice that the signal is spreaded, the resultant signal is spreaded, and its value will be equal to t, its time duration will be TB equal to NTC. Okay. So let us analyze this, analyze the value of this processing gain. So for that we want to calculate bandwidth of the spread signal and bandwidth of the unspread signal. So bandwidth of the spread signal is given by 1 by Tc. We have the duration of the spread signal is equal to Tc. So its bandwidth will be 1 by Tc. Bandwidth of the unspread signal will be 1 by Tb because its duration is Tb. So its bandwidth is equal to 1 by Tb. And processing gain is equal to bandwidth of the spread signal divided by unspread signal. So we will get 1 by Tc by 1 by Tb, that is equal to Tb by Tc. Thus the longer we make the PN sequence, then larger will be the processing gain. So here you can notice that processing gain can be improved by reducing the value of Tc. Actually Tc is the chip time. In the case of a C of t, that is PN sequence, each symbol constitutes the time period Tc. So it can be known as chip time, and processing gain can be improved by reducing the value of Tc, or if we are increasing the period of this PN sequence, then that means a large number of bits can be included in this so that Tc will be reduced. So processing gain can be increased by making the longer PN sequence. Next is probability of error. Actually in the case of BPSK, we know that the probability of error will have the equation 1 by 2 ERFC root EB by N0. This is the basic equation that we have studied in the case of BPSK. Okay. And here EB is the energy per bit, and we know that EB here we know that in the case of a white noise, power spectral density is N0 by 2. Okay, N0 by 2 is the power spectral density of the white noise. And in the case of direct spread spectrum binary PSK system, the interference or noise can be treated as a wideband noise signal with a power spectral density N0 by 2, and in that case we can write the equation this spectral density N0 by 2 equal to JTC by 2. And 2 and 2 get cancelled, so we will get N0 equal to JTC, where J is the average interference power and TC is the chip duration. If we are substituting that value, that is N0 is equal to JTC in this equation, you will get probability of error equal to 1 by 2 into ERF's root EB by, instead of N0 we can substitute JTC. So here the error probability, you can see that error probability decreases when this value increases. So this is complementary error function, so error probability decreases when this value increases. Okay, and probability of error increases if this value decreases. That is, this is a complementary error function, so when its value increases, probability of error decreases. When this value decreases, probability of error increases. Okay, so probability of error increases if this value decreases due to increase in the average interference power or the chip period TC. Okay, so in order to increase the probability of error, we have to reduce this quantity. This quantity will be reduced by increasing the chip period TC or increasing the value of J or interference pattern. But it will affect the entire system. Okay, so we cannot increase the value of TC or J beyond a certain limit. Next is anti-jam characteristics. Jamming margin is defined. In the case of anti-jam characteristics, we have to define jamming margin. Jamming margin is defined as the ratio of the average interference power J to the signal power PS. So J by PS will give you the jamming margin. For that, let us discuss about the energy per bit, that is EB equal to PS into TB, where PS is the average signal power and TB is the bit duration. And we have the equation EB by N0 equal to, instead of EB we can substitute PS into TB by N0. And we know that N0 is equal to JTC, that is we have obtained from this equation, that is N0 is equal to JTC. So we can substitute for NTC. So we will get EB by N0 equal to PS into TB by JTC. Okay, so EB by N0 equal to, this can be rearranged as a PS divided by TS into TB by J. Okay, so here you can write it EB by N0 is equal to TB by TC into PS by J, and this quantity is processing gain. So we can substitute as EB by N0 is equal to processing gain into PS by J. So we can rearrange this equation, that is J by PS equal to processing gain by EB by N0. So we can write that jamming margin in the decibel value is equal to processing gain in dB minus 10 log EB by N0. So this value this value will be equal to EB by N0 equal to processing gain into PS by J, and PS by J value is equal to, what is jamming margin? Jamming margin is defined as the ratio of the J by PS. So this J by PS will be jamming margin, this is jamming margin. Jamming margin decibel value will be equal to processing gain in decibel value minus 10 log 10 EB by N0. So this is how we are obtaining the equation for jamming margin. Okay, so that's all about this characteristics of the direct sequence spread spectrum with the coherent BPSK. There are 3 characteristics. Okay.